It's a topic we'd rather not think about. Where does last night's dinner go when we flush it down the drain? While you may already be grossed out just thinking about it, this question leads way to a significant subset of civil engineering and a massive amount of public funding. Just like all dogs go to heaven, all drains in a city lead to a wastewater treatment plant where that wastewater gets turned back into water that we can drink. Now, you may be thinking that you'd rather just let bygones be bygones and not think about this nasty part of real life. But here's the thing. Chances are you've drunk water that was waste at some point, so you might want to take some time to understand this engineering process that makes dirty water clean.
When you take a shower or flush the toilet, what happens to the water? Water and waste wash down the drain of homes, businesses, and industrial facilities flows through a network of pipes called a collection system. According to the U.S. EPA, there are about 800,000 miles of collection systems in the U.S., along with 500,000 miles of private laterals, which connect properties to the sewer system. Water typically travels through pipes by gravity. Once pipes get too deep, a pump or lift station moves wastewater into a new section, and water moves downhill again. Many older cities have combined sewers that convey both stormwater and sewage. A large storm can overflow the sewer and greatly increase the volume of water reaching the plant. Wastewater travels to the 16,000 publicly owned water resource recovery facilities, commonly called wastewater treatment plants, that serve over 190 million U.S. residents. The first part of the treatment process is called the headworks. Influent screens filter out large debris like rags, cans, and other trash, represented by the yellow spheres. The removal of large debris helps keep pumps and pipes within the plant from getting clogged. The trash removed from the screens is collected and disposed of at a landfill. The goal of the headworks is to remove inorganic matter from the wastewater. Inorganic matter includes items like trash, sand, or gravel, basically material that did not come from a living creature. The next stop within the headworks is the grit removal chamber. Grit is made up of large, heavy particles like sand or eroded cement. Water flows slowly through this tank, keeping organic matter like food, waste, bacteria, or excrement in suspension, but giving the heavier grit a chance to fall to the bottom. As grit settles out, a rake runs along the bottom of the tank, sweeping the grit away. Removing grit early on is important because it is abrasive and can erode mechanical equipment. It can also build up in later treatment processes. Though not shown here, flow monitoring occurring in the headworks helps operators prepare for volume and velocity of water entering the plant. Based on this information, operators can add the proper amount of treatment chemicals and allow adequate
Yeah, and it's probably travelled maybe 10 or 15 k's to be here at the most. This structure up here is our inlet works. It'll receive about 6 or 7 megalitres a day. So what happens at the inlet works is we're taking out the solids basically. So any like particulate stuff that's come, gone through our pumps, it's up there and it's going into a band stream. That band stream is like, a rotating screen with holes in it through which stuff passes. The holes are about 5 millimeters, so anything bigger than 5 millimeters is going to get picked up by that band stream, and it's going to go up and washed off at the top with some nozzles. Those nozzles are going to push out the bits of stuff that's got stuck on that stream. Screw presses. There's one up here, and there's 2 over there. So once that flow passes through the band stream, it's going to go into a grit collection vortex, which is just like a pretty much a propeller around this big like circular tank. And as that what remains of the solids gets forced to the outside, the velocity around the edge of that is obviously going to drop to 0 around the wall, and rather than spinning around, it's going to go settle down the bottom. We've got 2 stages in our odor control unit here. Usually you'd only have one. That first taller green vessel is actually a biofilter. So there are like live organisms in there which are munching up hydrogen sulfide, which is the main cause of odour. After it goes through there, we've got activated carbon in this smaller one just here, and that's like the final stage. It just scrubs it before you suck all of the air and punch it out this vent hole just that we're standing next to right here. So biofilters are great because you don't actually need to do much maintenance on them, but they can't handle a massive influx of odour all at once.
The water now travels on to secondary treatment. This part of the process removes nutrients like phosphorus and nitrogen, which helps keep rivers and lakes clean. Algae thrive in waters high in nutrients. When bacteria feed on algae, they use up all the oxygen in the water, creating dead zones that cannot support fish or other aquatic life. However, nutrients are also a valuable resource, particularly for agriculture, and can be recovered through the treatment process. The first secondary treatment stop is the aeration basin. Unlike primary treatment, this part of the treatment process relies on biological action rather than physical separation. Blowers generate oxygen that is distributed through a network of pipes into the aeration basin. Oxygen generated by the blowers is used by hungry bacteria, as shown in green. They feed on the solids, reducing their volume and removing nutrients. Next, water goes through secondary clarification, which works similarly to primary clarification. Again, solids are sent to the solids treatment process, and water moves on to be further purified. Some of the solids, known at this point as activated sludge, are sent back to the aeration basin. This activated sludge helps maintain healthy populations of beneficial bacteria that reduce solids and remove nutrients.
Now, aerobic zone. Now, just to make it a little bit more simple for us, this is where my knowledge of treatment plants starts to get a little bit hazy. So I'm going to run you through what Tom's given me, and then if you have any specific questions about what's going on, the chemical reactions and such, write them down, think of them, save them from Tom, because he's really going to be able to tell you all of that. So we've got two stages here. That train along there, closest to our inlet works, is our anaerobic zone. And in the middle here, we have our aerobic zone. Now, just to make it a little bit more simple for you guys, we're going to start talking about our aerobic zone. The purpose of this is to remove nitrogen. So you do that by adding oxygen. The oxygen is added basically with a big sort of like lawnmower paddle underneath there, and it's turning it up just like a wave in the ocean. When that crashes, you see all of the oxygen, all of that foam. So that's what's happening pretty much underneath us. Clarifiers, which was a great way to get grit and carbon out before it went through anything like a screen. But I'm told that back in the day they cared a lot more about the carbon nutrient in the influent than they did phosphorus and nitrogen. Now that they care about nitrogen, you sort of want a bit of the carbon in there for that bioreactor. So not many of the newer plants will have. What these secondary clarifiers do is that smaller circular area in the middle will be filling up with the water that comes out of this bioreactor here. And we're dropping down to a much slower sort of time for that water to rise through these clarifiers. Tom tells me it's around 1 metre an hour for the water coming in there to rise up, which is slow enough for the activated sludge, which is just heavier than our water, to biomass, which is mostly your bugs, but you've also got a little bit of any solids and stuff that's in there that didn't get screened out.
Before coming to the clarifier or after clarifier?
I was told this, and I'm going to say before the clarifier, but double check with Tom. The water filters through the belts. Water is recycled, put back in there, but some of the bugs, some of the extra solids that haven't been filtered out get basically just sort of pressed in the belt and churned out at the end. You'll see, we might walk around the other side, there's a big screw which will convey it all up into a big tank, and that is just, pay through the bloody nose to get that taken off and dealt with. It can be used as fertiliser or in fertiliser. but we don't sell it. We actually pay to have that taken out somewhere near Toowoomba, I think. So there's a lot of improvement for particularly this dewatering the waste activated sludge.
Final step, disinfection. This step removes any remaining bacteria or other microorganisms that could cause illness. Chlorine disinfection is the most widely used method.
So the idea of this is to remove those last pathogens. This is the only, they all have chlorine contact. Chlorine is one of the ways to remove the nasty diseases and all that. You can also do it with ultraviolet.
Yeah, that's painful, but
yeah, I mean, so
I've done it before.
Yeah.
The quartz lenses, and also it depends on the clarity of your water as well. That will also affect it. It's just, yeah.
I mean, yeah, it's all probably much of a muchness, but for whatever reason they've gone with the chlorine here. Guys, this is the opposite of your bioreactor, where you want the water that's coming in being churned around and mixed and diluted. You want the opposite to happen here. So think of like a cubic meter of water. You sort of just think of that as one slug of water, and you want that to spend a certain amount of time, without being sort of mixed and diluted, moving through those different channels as it works, so back and forth. That's because after the chlorine gas is dosed in at the start, you want that to have a certain amount of contact, hence chlorine contact tank. So, there's a flow rate going through here, and there's a certain amount of time which that chlorine actually needs to be, contacting. That goes through there. The chlorine sort of treats it all. You don't want that chlorine going out into the environment if you can help it. This is actually the only plant where we do a bit of dechlorination. Most of our other plants just put sort of mildly chlorinated water back in, and it doesn't do too much harm. Obviously, there's not a whole heap of requirement for it. Overseas, I think there's much more stringent requirements about chlorification, but I think in Queensland